Okay, so here we are in an IC design testing lab, and I have with me Balaji, and let me allow Balaji to introduce himself.
Hello, I am Balaji. I am pursuing PhD under the guidance of Professor Janak Raman in IIT Madras, Chennai, in the Electrical Engineering Department.
Okay, so Balaji, you are sitting in a hardware lab, right? So I assume you are doing some hardware related work, right? Can you briefly just tell us what kind of hardware work you're actually doing?
In this lab, we work with ICs. The aim is to design, fabricate, and test ICs end to end. We start from the beginning and till the testing, we complete it in our lab.
Okay, great. So, in some sense, I would say this is as hardware as it can get, right? It is, it is the definition of hardware work, right? Because what you said was you're designing an IC and we send this out for fabrication, right? So, where do you fabricate these ICs?
So, we fabricate, this IC right over here is fabricated in TSMC, Taiwan.
Taiwan, right?
Yes.
Okay, so we send it to Taiwan, they fabricate it, they send the IC back to us, right? And then you're going to do something more with it, right? And then you're going to test it.
Correct.
Okay?
So we need to characterize the IC for the performance and test it for the results.
So the IC that comes is something that you cannot just test. So what is it? I mean, I see that you have like a board sitting there, right? And that board also, did you design?
Yes. So in our lab, once we get the IC, we first design the PCB on which the IC sits. That's where it's located. But however, you can't control the IC directly. You need some, codes or FPGA to control it. So here we have an FPGA along with, of course, the power supplies as shown over here.
Okay, so I'll come to those components. So essentially, you're saying you got the IC back from TSMC, then you designed a board,
correct,
on which you are able to place the IC, and then you have to do something more in order to actually talk to the IC and test it and all that stuff, right? Yes. Okay, so I see, there is a board there, and what is that board connected to?
Yes, so this board is connected via this cable to what is called as a Z board. So this Z board, is an FPGA and an ARM processor together.
Okay, an ARM processor together, right? And what are these components that are sitting in, that are turned on here?
Yes, so these are the, power supplies, the DC power supply and, a precision power supply to control the chip, to give input and control and measure
the thing. Okay, great. So I see that you have therefore done a lot of hardware background work before which you can start testing the IC and all that. The aim of this discussion is to sort of let the viewers know how much of software knowledge does one have to gain in order to be able to complete such a task, right? I mean, it's very evident just by the look of it, there is a board, there is a hardware, there's a Z board, right? On that PCB that you have designed, you seem to have so many more components sitting there, right? Then you have a power supply, you have some sort of a computer that seems to be controlling all of this together. So there is enough hardware, right? The focus here, of course, is to understand what kind of software skills does one need, right? Or more fundamentally, does one even need any software skill at all to do hardware testing and design? Okay, so can you just walk me through the steps involved, right? In terms of, okay, what are you trying to do with this IC and how do you do it with what, hardware?
Correct. So, of course, to first answer your question, the IC cannot be controlled without the help of this PC sitting here and the Z board controlling, the IC. So, you need both of these components to run the IC. Okay. And all of them are pretty software intensive. So, I will, take you through the software stack to make you understand, what is going on inside.
Okay, yeah. So we can do that, right? So you have a presentation that you're going to take me through.
Yes.
Okay, great.
So so firstly, as you can see, here is our PCB with our IC sitting right in the middle.
Okay.
And in this particular case, this IC is a deep learning accelerator.
Okay. Fine.
So yeah, as I told you earlier, this is the host PC. This is the Z board,
Yeah.
and these are the power supplies.
Yeah.
So, I mean, what is this IC doing, right? It is trying to take a neural network and find out, perform inference on a neural network. That is the aim of this IC.
So usually this thing is done in software, but you are trying to build something known as an accelerator. So the chip
Correct.
is trying to do this
Yes.
for you.
Yes. Usually, you use Python, which runs on a PC which is commercially available, but we are trying to accelerate that, to get more energy, efficiency, and so on.
Okay, fine. Right.
Yes. So, here is one example of a neural network. It's
Okay.
a simple network, with 2 layers, and the data set in question is MNIST. So,
Okay.
here it is a data set of handwritten digits from 0 to 9. The aim is to recognize, when presented to the IC, right, you
Yeah.
need to find out which digit was presented to it. It was a
Okay, so it's like if I write a digit
Yes.
like this and give it to this chip, right?
Yes.
Provided you have loaded this neural network on it,
Correct.
it should be able to tell me of the 10 digits, 0 to 9,
Correct.
which digit was handwritten.
Which digit was handwritten? Exactly.
Okay, very good.
Exactly.
So, right.
Yes. So, this is a very simple example of a neural network.
Okay.
Again, we implement more complex networks with, several layers, which is a deep neural network,
Okay.
which has, many more layers than a simple
So-
2-layer network.
Okay, so by deep neural network, you mean take the output of one layer, feed it to the next,
Correct.
and this keeps going on.
This
right?
keeps going
And you
on.
have many such layers. It's not
Exactly.
just 2 of them.
Exactly.
Okay, great.
Exactly. Right. So, first of all, to get all of these weights and these parameters set up, you need a Python environment where you have an option of training it in Keras, TensorFlow, or PyTorch, which are different platforms in Python.
Okay, so straight away you have already introduced one software language called Python,
Correct. Yes.
right? And okay, so these are these I assume somebody has written it, and we are trying to use it.
Yes. So
Right.
we are trying to use a pre-trained network in one of these platforms. Let's say in our example it is PyTorch. We have chosen PyTorch.
Yeah,
to-
but in PyTorch, for example, the training code
correct.
was written by somebody else.
No. The training code was it was a pre-trained network. In this case, we are using it for inference. But in any case where you want to train something, in that case you need to write that code all from scratch by yourself.
Okay, so
which is
there-
a software, more software intensive.
Okay, so you first so even though your hardware, you need hardware knowledge to do something, the application itself may first of all demand that you know some software language.
Yes.
First
Yes.
of all,
Yes.
right? Okay, great. So therefore you have to know Python.
Exactly.
Okay, right.
Yeah. Moving forward, let's say we want to see what is the complexity of this problem, right?
Okay.
So what is happening? Inference is giving these images one at a time
Yeah.
to the chip, feeding it in, and then finding out what the chip has to infer what digit it is, right?
Yeah.
In this case, there are 10,000 testing images that are to be given. And as I told you before, a deep network has many layers. So these 10,000 images needs to go through all these layers and finally give you the result.
So each one of these 10,000 will go through all these layers. You will recognize what that digit is,
Exactly.
and you do this 10,000 times.
Exactly.
Essentially. Okay,
Exactly.
fine.
Exactly. Yes. So, in our case, we have taken, this PyTorch trained network with
Okay.
its weights,
Okay.
its images, all of that. And, we have stored it right in this SD card. As you can
So
see.
these weights are essentially some numbers.
Yes. So
some
these
numbers.
weights are some
Some
parameters
numbers,
of
right.
the network.
Okay, and you have stored it into the SD card of that FPGA,
Exactly.
right? Okay, fine, right.
Exactly. So, once you store it into the SD card, the connection interface between this setup, the Z board, and your chip, helps you to stream data
Okay.
and obtain the result as well.
Yeah, but the streaming of data is also not, it's not something somebody else wrote. You have to write it.
Yes.
You have to write it.
Streaming of data is an essential component where you need to write a lot of. I will be going
Okay,
through them.
great.
in the-
Right. Okay.
Correct.
Go on.
Right. So okay, now we'll look at what is to be written in order to stream data from one place to another.
Yeah.
Right. So first we'll start off with what is to be written on the host PC.
Okay.
Right. So the host PC is connected through an USB to this Z board first of all.
Okay. So this host PC, by the way, is running on Linux or Windows or what?
In our case, it's Windows.
But it can be
in
Linux.
In most cases, it's Linux.
In most cases, it's Linux. And
Exactly.
essentially, you basically you'll start off with some sort of a terminal.
Yes.
Right?
We will
From
start
there.
off with a terminal.
Okay, great.
We will launch a script from there.
Right.
Which will,
Okay.
Yes. So yes. So this host PC is connected to the Z board. The main function of this PC is to set up all the step by step sequencing of operations, right?
Okay.
So let's say the first sequence is turn on the the power supplies, turn on the measuring unit.
Wait. So you're now saying that power supply is also being controlled through some software on that PC.
Yes, because we may need to in real time change the value of voltages and measure out some values in real time. So we cannot have a manual interface.
So you don't want manual intervention at all.
No.
Okay. I understand. So let us say, okay, maybe you go on. I'll come to this part again. Okay, great.
Okay. So once you turn on all the power supplies, you will give a start or a sequencing step will be incorporated from the host PC using this UART connection.
USB UART connection.
Exactly.
Okay. Yeah.
Okay. So once that connection is set up, there are two more steps of coding styles that we still have to discuss, which help this the entire process. So the first style is the Z board, right? It runs on an ARM processor. There's an ARM processor right in the middle.
Okay.
This ARM processor waits for the signal from the host PC.
Okay.
And triggers a set of C codes.
Okay, so you said you needed to know Python first.
Exactly.
In order to even get your app, basic setup going, a neural network that can be loaded into the chip. Now you said there's an ARM processor on that Z board for which you need to know C.
Exactly.
You need to know C programming.
Embedded C, correct.
Embedded C programming.
Exactly.
Okay, great.
Yes. So, once the go signal is given from the host PC, the internal C code start executing.
Okay.
But the C code runs at a very slow frequency, which is the ARM processor's frequency of about kilohertz or very
something much slower.
Much slower, right? Right. So the idea is we need to move on to something faster, for which we have an FPGA on this Z board.
Okay. So now there's another hardware. So there's an ARM processor. There is and the ARM processor actually, if it is essentially like your desktop processor.
Yes,
right? It's another another processor, co-processor that is sitting.
Exactly.
Then you have an FPGA which is where you're going to offload some high-speed tasks.
Exactly.
Okay.
Exactly.
Great.
So in order to offload these high-speed tasks, we need a separate language again, which is Verilog.
Which is Verilog.
Yes.
Okay. So Verilog is a hardware description language.
Yes.
Okay, but it's still a software, right?
Yes.
In some sense, it is still a software language.
It's still a software language.
Okay. So you started with Python, you came to C, and now you are talking about Verilog.
Yes.
Okay,
exactly.
Great.
So then all of these timing critical signals are finally passed through this UART cable completely without any manual intervention.
Without manual intervention again. Okay, great.
Correct. Okay, so now once this is passed there, let's say I need to observe some signals.
Yeah.
Right. I measure them again through this precision measurement device, which is connected using MATLAB, and we retrieve the data like that.
So you can again control and even measure, like you gave an input voltage.
Yes.
You can also measure a voltage through the software in MATLAB.
Exactly.
Right? Again,
Exactly.
which is some code you have to write
Exactly.
to control that.
Exactly.
Okay.
Great.
Great.
And if it is a digital signal, it will be fed right through these signals and come back to the Z board, and it will go back through the USB UART to the host PC itself.
To the host PC. Okay.
Exactly.
Fine.
Yes.
Great.
Okay. So I mean, how do these digital signals that are sent back from the chip, how are they interpreted, right? So literally you will get a hex file as you see over here.
Okay.
And this is not intelligible.
Okay.
The idea is we have sequenced these bits in a way where we have some we know where is the start and end point of a particular operation, using which we write a code to retrieve what is.
Okay, so let's take a step back. You started with Python code which has some weights.
Correct.
Now that was converted to some binary number that
Yes.
needed to be written. So if you take a particular neural network layer, right, what is the size of this file that you have to write? The weight file.
Yes, so let's say we are running about 500 images at a time.
Okay.
The size of the file will be close to an MB.
So 1 megabit.
Yes.
Okay. And the weights itself, right? I mean, so how big is that chip? How many memory cells do we have?
The weight, the memory cell is 400 KB.
400 KB.
Yes.
Okay. So you can store up to 400 kilobits of
information in the chip.
that chip. So you need to first of all stream in.
Yes.
And all these 400 kilobits cannot be streamed in parallel.
No.
Right? It has to be streamed in serially.
Yes.
Right? One by one.
Yes.
Right? So you do a serial, somehow streaming in. That is written. And then you need to feed one image at a time.
Correct.
Right?
Correct.
And you said that 500 images is about 1 MB.
Yes.
Okay. Great. Yeah. Proceed.
Yeah. So this finally, after deciphering what is there in the script, in the text file that you receive, you will be able to make sense of it, and finally be able to predict.
So this language again is what? This looks like what kind of language is this?
So this is again MATLAB.
This is your back to MATLAB.
Yes, we are back to MATLAB.
You're back to MATLAB.
The host PC that receives the
data, right? Yeah. And then you're doing some recognition with it. You're making sense of that data, right? Okay, so how big is this file that you get out of this chip actually?
Yes, I mean, if you see in this page itself, there are about let's say 70-80 lines, and you can see the scroll bar over there.
Yeah.
And it's pretty huge. So it probably is 70 into at least 1,000 more lines.
1,000 more lines.
Yes.
So you have essentially it's not uncommon to expect that the output from a chip could land up with 1 million lines of information.
Yes.
Right. And this also means it's impossible to even open this in Excel or something and just see. It won't even open.
Yes.
So you need a scripting language that can process such a large file line by line.
Yes.
And get the data.
Yes. For instance, this MATLAB code itself, calls an awk shell script, to process some of these lines and then.
Okay, so there is an awk script internally which is actually processing this file. It's not MATLAB.
Yes.
You're not doing an F open of this full file.
No.
Okay, very good. I understand. Right. Yeah. Okay, go on.
Okay, so this is all about how we test the chip after it's come back from fabrication. But
before we get into this, right? So when you joined IIT Madras, what language of programming language did you know?
I mean, I knew a very basic amount of MATLAB, which is 2% of what I know right now.
Okay, but what about C and?
Yes, a very basic version of C.
Let's say Python.
Python, no idea.
Nothing.
I didn't know Python.
So, did you take a course to learn Python?
No, I did not take a course. I looked at some online resources for some specific application that I needed, and I got
it. So you are basically saying, first of all, there is nothing sacrosanct about a new language.
Yes.
You pick up something. You don't have to pick up the entire language. First of all, you are going to pick up the skills needed for that particular task.
Exactly.
Do it and finish it.
Exactly.
Right. So therefore, you have picked up in the process. You seem to have picked up Python. You seem to have picked up. You improved your levels of C coding. And also improved your levels of MATLAB coding. Okay, fantastic. Great.
Yes.
Okay, so what is this? So you're saying, okay, but I thought chip design was again a purely hardware task, right?
No. So again, chip design is okay, let's say if you have to build a simple transistor circuit,
Yeah.
all that your CAD tool, you can visualize the transistor, but
Okay.
after that, how do you design it?
Okay.
Right? So all of that has a huge software stack even in the design process.
Even
as
for
well.
design.
Yes.
Okay, great.
Yes. For example, let's say in one of our earlier chips, right? So let's say you need to design such a 4 transistor circuit. First
Okay.
of all, how is this transistor circuit even represented?
Okay.
This is represented using something called as a netlist.
Okay.
And the language we are using is Spectre. So it's a Spectre format netlist.
Okay.
Right. So this netlist is nothing but a description of these connections that we have made. The graphical connections are translated to lines of statements. So once you have this netlist, how do you simulate or design, right?
Yeah.
So again, it is completely a CAD exploration, where first, let's say you need to design some DC sources.
Yeah.
Give some inputs first of all.
Okay.
And give some inputs as waveforms, right? You need to give some waveforms and DC sources to analyze the behavior. For such a DC file, I mean, you need to write a DC file for it.
Okay.
In the sense, this file is a description of those voltage sources given to the circuit.
Given to the circuit.
Right.
Okay.
So that file is to be written by the designer.
Okay.
Similarly, even a vector file needs to be, again, vector file is nothing but step by step, timing instant.
So at a particular time instant, what the value is?
Exactly.
So time value pair, right? That's all it is, right?
Yes.
Okay. So what is the problem in manually writing this?
Yes, I mean, so for a simple circuit like this itself, it is very tedious to write it manually.
Okay.
Right? I mean, let's say if the voltage of a particular node changed, what would you do? You need to go back to that manual file and type it out yourself.
Okay.
Which takes a lot of time.
So essentially, what you want to do is anywhere where there is a pattern,
correct,
you want to automate.
Yes.
Right. Essentially, right? You don't even want to do something twice.
No.
You just want to automate that and just be done with it.
Yes.
Right.
Correct.
I also see there is a certain advantage because if you make a mistake in the manual process, you had it. You have to go back and redo the entire work manually.
Exactly.
But if it is an error in your code, you fix it once and run it again, you'll get the output like that.
Yes, it takes some time to bring up the code, but once it's done, it's reusable for many design applications.
So essentially, I would say programming, automating is actually a way of life. It's not about
exactly.
It's about a way of thinking.
Exactly.
Right? It's not about the language. It's not about the and I have another question for you. Is whatever you have implemented, is it the most efficient way in which you have implemented all of this?
No, definitely not. So the codes that we write are something that we come up with using some resources that we have. It may not be optimal. We try to make it optimal by revisiting those codes, now and then again. Right?
Okay. So again, what you're saying is you basically say that you just, for the task given, you figure out what is the simplest way to do it.
Yes.
And
at first,
initially, and then when you hit a bottleneck, you speed it up, you improve it. So you're not seeking for the most optimal code or the algorithm in all this automation, because I think okay, I understand that. So essentially, you're saying now let's again list out the languages that you had to sort of learn here. You said there's a DC file, so this you said was
again
Spectre or Spice.
Yes, Spectre or Spice.
Whatever. Okay.
Correct.
Then you said there's a file that internally. So if you were to generate this file, the vector file,
yes,
what language would you write this in?
Yes, again, so to generate these DC files and vector files, I have a script that does it for me.
Okay.
Which is a Python script, where you just say this is the voltage, name of the node voltage instant, and this is the value. So I just give name value pairs, and it automatically creates that the script that you see here.
Okay.
Right? Exactly. In a similar manner, we use a combination of skill. I mean, in a similar manner, you can also get your waveforms also
Okay. So
designed.
So Python again,
Correct.
which seems to be a common language between what you're doing in design and testing.
Exactly.
Then there is Skill and Ocean.
Yes.
These are again two proprietary languages, I guess.
Yes. So Skill and Ocean are used to automate for simulations. Right?
Simulations.
So let's say if I have to set up a simulation where I need to measure out. So once I've given the inputs, right?
Yeah.
We've designed the inputs. We've given it using files.
Okay.
You need to use a bash script first of all to set up the specter. You should say ask the specter to take this particular netlist with so and so inputs and then run it and give you an output.
So you use the word bash.
Yes.
So you also use shell scripting there.
Yes. So
shell scripting is mandatory.
yes. So shell scripting is one layer. We keep using it now and then for.
Okay. So it's basically the base.
The base,
right?
Exactly.
From the terminal, all of this
Exactly.
essentially runs.
Exactly.
Okay. So therefore, again, I'm assuming that you did not do a course to learn bash or shell or skill or ocean.
No.
You just picked it up.
Yes.
Right? And so what is it that allowed you to pick up all this software, though they are all different languages?
So initially I went in the manual approach where I gave inputs using a dialog box. The software also has a dialog box where you can give inputs. But after a point, when you have to revisit those circuits, it just becomes too waste of time to revisit it like that.
So it's unmanageable. It becomes
yes,
very quickly
as
becomes
things
unmanageable.
grow. In the initial phase, it's good.
Yeah, I understand, right? So it's okay to make like 2 transistors, 1 measurement, you can get away manually.
Yes.
But the moment I have 20 transistors and I want to make 1,000 measurements,
especially with the chip which has million
transistors, the only way is automation.
Automation,
right?
Exactly.
Okay, great. Okay, yeah. So you have anything else?
Yeah. So
okay, this is excellent. So I think the message you have unambiguously conveyed is without software, all your hardware is just useless.
Yes.
It's basically nothing. So if you notice here, unlike what we see in the other ICs, it's not like you can go and measure a pin and see it on the oscilloscope and say that the chip is working. It comes out of huge log files that come out of the chip, and unless you know how to parse and process these files in software, there is no way that you will be able to even do anything useful with your hardware. And from what Balaji says, even the design process requires so much of software knowledge. And I'd like to repeat that software doesn't mean languages, it doesn't mean syntax. Right? Nowadays with ChatGPT and other things, you are free to learn syntax of a language through examples and asking for sample code. The idea is for you to be able to think of an automation algorithm that will enable you to do the task.
Exactly.
Right? So I think with that, let's just take home the message that you just need to be an expert at software and hardware if you were to do anything in the hardware domain in electronic systems. Thank you, Balaji.